Newton's law of cooling. What happens to the temperature if you, let's say, leave a cup of hot coffee out on the counter at room temperature? Perhaps put leftover dinner in a refrigerator and save it for later. If you put an ice cube in a soda and let it sit for some time. Choose one scenario above, make a quick sketch of the temperature over time, and ask yourself, do these situations remind you of anything that you have learned previously? I'll just take the first one here, and I'll make a quick XY axis. And I'm going to put here, I'm going to put a line y equals R, where R represents the room temperature. So if I put a cup of hot coffee on the counter, it's going to start hot and quickly cool, and then eventually it's going to wind up right about to where room temperature is going to be, and that's as cool as it's going to get, whatever the ambient room temperature is. So does this remind you of anything you have learned previously? Well, the conclusion is the object, whether it's the coffee or the ice cube, cools or warms to the surrounding temperature over time. The temperature of the object is limited by its environment. The simple inhibited growth formula applies to the situation in which P is the maximum or the minimum limiting factor. In the case of the coffee, the limiting factor was the room temperature, the ambient temperature of the room. Now note that Newton's law of cooling also applies to warming. These basic sketches may resemble some of the following. So you'll notice here the temperature is dropping over time till we approach room temperature. The ice cube is going to warm up as it gives its energy off to cool the surrounding soda, and then eventually it's going to hit room temperature and level off. Example number 3, Newton's law of cooling. A bowl of hot soup is brought into a room which has a temperature of 20 degrees Celsius. The soup was originally 80 degrees Celsius, and after 2 minutes it is cooled to 60 degrees Celsius. How many minutes pass before the soup cools to 40 degrees Celsius? So our first step is to identify and substitute in the given information, and we are substituting into our general equation for simple inhibited growth. Y is equal to capital P minus the quantity, P minus Y sub 0, times e to the negative kt power. And it tells us right in this sentence that the soup was originally 80 degrees Celsius, so my Y sub 0 is equal to 80 degrees Celsius. It also tells us that the room temperature is 20 degrees Celsius. So my capital P, my limiting factor, is the room temperature, or the ambient room temperature, that is as warm or is as cold as the soup is going to get, because it's influenced by the outside temperature. We're also told that after 2 minutes, we're given a specific condition at T equals 2. So after 2 minutes, the soup has cooled to 60 degrees. So Y sub 2 is equal to 60. And then we're asked how many minutes pass before the soup cools to 40 degrees. So that's why here I have Y of question mark, because we're trying to find out the value of T when the soup is equal to 40 degrees Celsius. So making the appropriate substitutions where Y is 60, capital P is 20, Y sub 0 is 80, and T is equal to 2, we solve for e to the negative k power. And getting to our algebraic steps, we get to this step right here. 2/3 is equal to e to the negative 2k power. To go from the step to the last step, what I did was I took the square root of both sides, or I divided both by 1/2, or raised it to the 1/2 power would be more accurate, and I get 2/3 to the 1/2 power is equal to e to the negative k. So I am going to take this value, 2/3 to the 1/2 power, and I substitute that in right here for e to the negative k power. So here you see what was e to the negative kt becomes 2/3 raised to the t over 2 power, making the substitution that we did before. So now I do substitute e the value for e to the negative k, and I substitute y equal 40 into the equation to find out how many minutes has passed before the soup cools to 40 degrees. So we make our substitutions, and using our algebraic steps, we get to this step right here. 1/3 is equal to 2/3 t to the 1/2 power. And on the next step, you'll see I have the log of base 2/3 of 1/3. What I do to solve for t is I take the log of both sides, and that's how we get, and by the way, I'm using a base of 2/3 since that's the base here. So this is log base of 2/3 of 1/3 is equal to t over 2. And then I multiply both sides by 2 to get 2 times the log of 2/3 of 1/3. I said that wrong, I'm sorry. 2 times the log base 2/3 of 1/3 is equal to t. And we find out that t is equal to 5.419 minutes. Let me take a moment and explain how I went from this step to this step. How did I take 2 times the log with a base of 2/3 of 1/3 equal to t and find out an actual value of t? Because for some people that might not be too obvious if we don't know our rule of log. So if you know these rules, please indulge me as I explain this further step. So here I have the log base b, any base of x, is equal to the log of any base a of x divided by the log of any base a of b. And for our particular problem, I'm going to let x equals 1/3 since we are finding the log of 1/3. And our base is 2/3, so this is log base 2/3. And I'm going to choose a value for a which is relatively common. A is going to equal 10. Since the log base 10 is very common with tables, our calculators are set for that as a default. So this will make it easy for us to find the value. So making the appropriate substitutions, we start out with the log with a base of 2/3 of 1/3 is equal to a log base 10 of 1/3 divided by the log base 10 of 2/3. So I do the arithmetic here on a calculator. Multiplying it by 2 gives me the result that t is about 5.419 minutes, or to answer our question specifically, it takes about 5.5 minutes before the soup cools to 40 degrees Celsius.